Record on this computer. Okay, so yeah, before we get started with the lecture, any questions about the course, where we are? We're week 8, so basically almost towards the end. So we have this is Thanksgiving week, so typically pretty light, but then we've got basically 3 more full weeks of MRI. I will discuss project 2 at the end of the lecture. If for some reason I forget, Amin or someone remind me, just say, can you say something about project 2? As everyone, I think, saw the announcement, there is homework 5 is posted now. You have till next Friday to do that. A lot of it's MATLAB grader problems. So you can start working on those and get immediate feedback. There is a written offline component to all of those, especially with the prevalent use of ChatGPT. We're trying to figure out what to do with that. But probably next year we'll have different policies. Any questions on the course logistics or materials before we start in on this lecture? No? Okay. So let's get started then. So today we're going to review K-space trajectories and pulse sequences and get into sampling, aliasing, and resolution. So the idea is by the end of this lecture, hopefully, you'll have some sense of what actually goes on at the MRI console, what the parameters that the technicians or the doctors are putting in. And so that's a basic understanding there. So just to remind you where we are, we've covered polarization, excitation. So we're really in the encoding integration part of MRI, essentially the part where we make the images. And just to remind you, the main job of the gradients is to create phasor patterns, okay, that have spatial variations to them. And so, for example, as we said before, if there's no variation in the phasor pattern, then that's kx equals 0. Here, the period is 8 delta x, so it's the spatial frequency is 1 over 8 delta x. Here, the spatial period is 4 delta x, so the spatial frequency is 1 over 4 delta x there. And then what we talked about is in MR, the signal that it requires a function of time is equal to the magnetization at time equals 0 when we excited it. There's going to be, and now we're just talking about the transverse magnetization, so there will be T2 decay, which we'll get back to later. And the main thing with the encoding is there's this phase term. Okay, so this phase depends on both space and time. At every point in time, we want to impose a spatial pattern in space. That's our Fourier pattern. And then we vary that with time. So at every point in time, we're going to another different point in Fourier space. So if we write out what this phase is, it's got an overall term, e to the minus j omega naught t. That's the overall precession of all the spins that are occurring, okay? And just to remind you, and related to the pre-lecture quiz, that omega is equal to minus omega naught t, okay? So that means as a function of time, the theta of precession is becoming negative, okay? So I think for those of you on problem 1 of, it's for me, it's problem 1, but I guess you guys get it randomly. But there was one where you asked the phase, right? And I think where most things, a lot of people got the number correct, but the sign incorrect. And so that's basically, you just have to remember, it's a clockwise rotation. Free precession is a clockwise rotation. All right. And then the other term we have is what we're talking about today, is this is what the gradients do. So the gradients actually impose the spatial pattern of phase. And then as the gradients change with time, it lets us visit different places in K-space. So for example, here, we're at kx equals 0, ky equals 0, okay? Here we're at kx equals 0. And is ky positive or negative here? What do you think? So as I'm going in the positive y direction, what's happening to the phase? Okay. Is going counterclockwise. So is does that mean ky is positive or negative? Negative, right? So for your homework assignment, that's going to be important for you to figure out positive and negative. And just remember, in this class, by definition, we're always looking at things of the form exponential minus j 2 pi kxx plus kyy, okay? And so that's the minus sign, okay? Just change the color here, whoops. Okay, so so the nice thing is once you've gone through all the math, then it turns out that the MR signal as a function of time is simply the Fourier transform of your object. And at every point in time, you're at some location, kx of t, ky of t. And the expression between kx and gx is really nice and simple. It's so simple that it's deceptively simple in the sense that it's so simple that you would think there's nothing to it, but in fact, there's a lot of flexibility. And so, as I said before, there's probably thousands, if not hundreds of thousands of ways of doing this that people have tried, of specifying the gradient as a function of time. But once you've specified it, then it's actually quite simple. You just take the time integral to that up to that point in time, multiply it by gamma over 2 pi, and that tells you where you are in kx, okay? So the gradients control our position in k-space. Okay, so just to remind you, this is like k-space here, right? We've got kx, ky, okay? Just a reminder, if I'm at some place in k-space, right? I have to think about the magnitude of this vector, right? The magnitude of that vector, okay? And that's just going to be kx squared plus ky squared, and 1 over that is the spatial period, okay? So I think some of you remember that formula, many of you did not. And so if you just remember that formula, that's pre-lecture, one of the pre-lecture quiz questions. And then the other thing is what you should have a fairly good understanding of is anywhere you are, if I'm out here in k-space, then the spatial pattern that it implies is just perpendicular, okay? So for example, this might be at coordinates 4, 1. So you just draw the coordinates, draw the perpendicular, that gives you the answer. So if you did that on the pre-lecture quiz, you would get the right answer. And if you did not, then you would get the wrong answer. So that's just, you know, sort of how you want to interpret that, okay? Today, so the main thing that we're going to talk about today is, the main question is, how do you go through k-space, okay? So today we're going to do spin warp, and that's what we started last time. Spin warp is you go line by line by line by line, okay? Now, in your project, you're actually going to do something different. You're going to go through k-space like this, like a square spiral, okay? Sort of in your homework, sorry, not in your project, okay? Although you could do that as a project too. You could look at different ways of going through k-space. So the design criteria are exactly the same for the trajectories, but just as a warning, and I'll emphasize later, what we do for spin warp is just one way of applying those criteria. If you apply those same criteria to the square spiral, you will not get the right answer, okay? Because it's not, what we do today is one application of those principles, but if you apply the correct principles, then that problem is going to be fairly straightforward, okay? And just as a note, for those of you who are doing the MATLAB graded problems, there's 3 problems. Each of them is designed to be done. You can actually do them in less than 10 lines of code for each one. So it's really not a matter of, you know, writing lots of code. Maybe ChatGPT can do it in less than 10 lines and check to make sure it's correct. If you use ChatGPT, we will be looking for a very clear explanation of why your code looks the way it does, okay? That's mostly to help you, because if you use ChatGPT, you're not going to learn anything from the course, all right? Okay, so let's go over the spin warp pulse sequence. So this is the building block of the spin warp pulse sequence that we looked at last time. And so essentially on the GX and GY gradients, we have these are called the initial dephasers, okay? They basically take us out to initial starting point in k-space. And then this is really sort of where the readout occurs. And so the basic building block is the dephasers take us out to a starting point in k-space, and then we zoom across k-space, all right? And as we zoom across, that's where we collect the data. So as we talked about last time, this is what a basic pulse sequence looks like. We imagine exciting the excitation, at regular intervals. We'll talk about that later, how to pick that interval. But for now, let's just say that each of these is putting the magnetization into the transverse plane. And then we repeat this readout gradient exactly the same for every repetition, okay? And then the main thing is the dephaser amplitude varies across repetitions. And so here we have a negative value of dephaser. So it's going to put us out at a negative KY value. This GX dephaser takes us negative KX. And so we start off here. We turn off the GY gradient. We only have the GX gradient on. And so now we zoom across K space this way, okay? And then for the next repetition, we go to the blue line. We acquire another line in K space. We have a different starting point because this blue one is half the amplitude of this cyan one. And then for the green one, there's no gradient played out. So we stay at KY equals 0, and we just go this way and this way, okay? So, and then you can imagine adding more gradients in the positive direction. So if orange is there, and then pink is there, okay? So that's basically how a spin warp pulse sequence works. And so for the remainder of this class, we're gonna really focus on talking about how do you pick the parameters of this sequence to go through K space to get a certain resolution and a certain field of view. Okay, so for example, let's say my object was a rect function, okay? So then we know the MR signal is just a two-dimensional sinc function, okay? So let's imagine we put a square object in the MR scanner and we scan it. So what would it look like? Well, what I'm going to show you, this is my object, and this time series is going to show you line by line what the MR signal would look like if that was my object. And then we're going to just take every line here and stack it into this, okay? So let's play the movie. You can sort of see little bumps there on the line. And then at some point it gets big and then it goes back down. And you can sort of see here we're acquiring a two-dimensional sinc function in 2D Fourier space. So let me play it one more time. Okay, so that's basically the most basic MRI pulse sequence you could have. You're just going line through line, and you're basically building up your information in Fourier space as you go. Okay, so as I said before, imagine Fourier space is just a grid. And the idea is you can go through that grid. I don't remember why this person has pigeons in here. I guess the idea is you can put the pigeons in any order you want, okay? So, so you could go through what we said is Cartesian. That's what spin warp does. You could go through square spiral, which you'll do on your homework, okay? You could go through zigzag, which is a very common pulse sequence in functional MRI, which is what I do. And you can also do radial, okay? So this is sort of like doing CT, okay? You're going radially through K space, right? This is actually the zigzag pulse sequence, which is used a lot in functional MRI. And the idea here is instead of going line by line by line, you just zigzag through as quickly as you can, okay? And so this allows you to do what's called snapshot imaging or rapid imaging. So just in one excitation, you get all the K space, and then you repeat that over and over again, right? And this is sort of what the pulse sequence looks like. So there's an RF pulse, frequency or readout pulse here. And so you see it's going up and down and up and down, and the phase pulse like that, okay? So this is certainly, if you're looking for projects, you know, echoplanar imaging is definitely a rich area to look in. There's actually even a project from many years ago that you can use as a template if you want to do that, okay? So that's all, we'll talk about later. Okay, so let me just, the gradients, it turns out, the moving of the gradients typically happens on the order of, we're switching them on the order of half a millisecond to a millisecond on that order. So that gives you frequencies in the sort of the kilohertz range, which means you can hear these gradients, okay? And that's actually a characteristic of MRI, which is essentially, it can be quite a noisy modality as compared to the other modalities. for researchers, it's sort of interesting because once you know what pulse sequences are, as you're lying in the scanner, you can actually tell what they're doing, right? You can say, okay, well, this is a diffusion sequence. This seems to be MT range, anatomical sequence. And so you can actually, if you know enough about MRI pulse sequences, you actually can tell what the radiologist is doing to you, right? But let's just play this movie for a little bit. I hope the sound is loud. I don't know if you can hear it online. Can you guys hear it here? It was bagpipe.
No.
Continuing problem with fMRI is synchronization of the stimulus with the scans. Imaging Research Center has addressed this problem by requiring the gradients themselves to issue audio prompts to the subjects.
Sound files can be directly recorded into the SGI. A C program is written to store the file in an array. It is then downloaded in real time into the gradient waveform memory using the pulse program shown here. Only a few lines of pulse program code are necessary to output the array to the gradient waveform controller. Shown here on the oscilloscope is an example of the current output of the gradient amplifier of the digitized bagpipe sound file. Here's a view of the Brooker Paravision pulse programming tool showing the 32 kilobyte digitized waveform of the Scottish bagpipes played out on the slice selection gradient.
Yeah, so that's basically using the MRI machine as a very expensive speaker, right? I mean, you have basically a $2 million speaker that's playing the Scottish bagpipes for you, okay?
Wallow. Wallow. Wallow.
Okay, so what they're doing there is, and this movie is on Canvas, so you can look at it. Essentially, no one really, some have tried this. I'm not sure how much it's used, but they're basically having the pulse sequence either do the acquisition. So when you hear the that's the readout gradient going back and forth. Okay, probably about 2 kilohertz or something. And then because they're looking at, I think, throat cancer or something in children, they want the person to swallow, and it's maybe painful to swallow, and sort of seeing their brain response to swallowing. And so instead of, typically what we do is we just hook up a sound file to the earphones, but for this reason, it's sort of cute. They actually have the MRI scanner telling you to swallow. Okay. So the idea is when you're in an MRI scanner, then when you hear the noise, typically that's the gradients moving back and forth. Okay. Okay, any questions before we move on to, yes?
What's the limit to how fast the gradients can split?
That's a good question. So basically, every gradient is specified with two things. You saw a little bit about that. In one of the mallet graders, we put a limitation on how big the gradient can be. I sort of was nice to you guys this year. I didn't put a limit on how quickly it could change. That would change the problem a little more. So that's what's called the slew rate. So basically, every gradient comes with a slew rate, which tells you how fast it can go. So there's a hardware limitation, but you can actually buy gradients that are like super powerful, but you actually can't use them. And the reason why is if I have a time varying magnetic field and I switch it really quickly, guess what? I have E equals minus dB dt. So that generates currents in the body, and that actually can be quite painful. In my experience, sometimes I'm in the scanner and it's like your face just starts twitching, like your muscles just start twitching. Like those things that people use to build up muscles, like they attach electrodes to their body and like their muscles twitch. Well, that's basically what the MRI system will do to you. And so it can be quite painful. I've been in things where like this muscle is just like so painful, it's like being contracted. So that's limitation. And there's also some concern, although we're still looking at, the field is reviewing the guidelines about, the main concern is whether it's going to stop your heart. Okay. Because, you know, zapping your brain, people are not so worried about, and people do it anyways. But if you stop your heart, then that's a big problem. Okay. Yes, question.
Sorry, you said pulse width is gonna stop your how?
The change in the DBDT, if that's too strong, that can create a strong enough electrical current that it will actually yeah, it could basically pace your heart, right? So so that's basically it's called peripheral nerve stimulation. So that is also regulated, and people are trying, that is really one of the limiting factors now, and people are trying to figure out how to get around it, but it's, yeah, question.
Another question I have is if you decrease the magnetic field strength itself,
Mhm.
for the frequency, does that like offset? Like if you're concerned with temporal resolution, for example, in a dynamic sequence versus spatial resolution, would that offset the peripheral nerve?
The main field is really hard to change quickly, simply because, you know, it's a huge thing, and it's at 3 Tesla. So I think one thing to think about is the main field is like a huge like tank. You're not going to change it very much. The gradient fields are on the order of Gauss. So for example, 4 Gauss per centimeter means that within a centimeter, the field changes by 4 Gauss, which is about 8 times the Earth's magnetic field. So those fields are just much lower fields. So we can change those. And those are simply with wires and things like that. Okay, but that's a great question. Anything else? Okay, so now we're going to move on to sort of the trying to put everything together. So we're going to try to put together our knowledge of the MRI pulse sequence, and then bring in some concepts from Fourier theory and sort of tie everything together. So the main thing that happens when you go to MRI exam is you need to specify the field of view, how large is the object, okay? And you need to specify the resolution, like what do you want your voxel or pixel size to be, okay? So those are 4 different parameters that you would definitely want to specify at every MRI exam. And so that leads to 4 different parameters on the Fourier side. It turns out the resolution is tied to how far out you go in K space. And so here we designate it as the width of Kx and the width of Ky. And then the field of view determines the delta, the steps you make in either Kx or Ky. Okay, so we're going to talk about how you go from these 4 parameters to these 4 parameters. Okay, so first we're going to give you a sense of this. So here is a object and its Fourier transform. Now here what I've done is I've just zeroed out every second line. Okay, so I've half the amount of data. And you notice that this is sort of, basically, if this is sampled at say 1, this is sampled at every 2 steps, okay? And so what you see when that happens is you get this aliasing, okay? So in this case, the brain repeats itself and overlaps itself, okay? And you can sort of tell, I mean, obviously, if you went to the doctor and they gave you this back, and if they said this was your brain, you would be concerned, right? You'd be like, this is why I have headaches, right? Because my nose is going into the back of my head or something. Okay, but that's not true, right? It's just what the image looks like. Okay. Similarly, if I take every other step this way, then I'd get aliasing in the y direction. So the image would repeat. And then if I take every other sample in Kx and Ky, then the image repeats both ways, okay? Both along X and along Y. So for almost every MRI exam, we want to reduce aliasing, okay? And what we're going to talk about, we're going to look at 2 ways of reducing aliasing. For this lecture, and probably some of the next lecture, we're going to talk about setting those parameters, delta K and WK, correctly. And then, but that's like 50-year-old technology. Like what I'm teaching you now is 50 years old already, or 50, yeah, 80, 20, 40 years old, let's say, okay? Then we're going to talk about what we actually do now to reduce aliasing, okay? So that's the roadmap. So let's talk a little bit about why we get aliasing in MR. So remember, if these are my spins, we can, for this course, we always imagine you're just starting off at kx equals 0. And then we take a step and you can sort of see this spin here is at the isocenter. He doesn't change, this spin doesn't change. This one advances, this one goes backwards, and so on and so forth. And we take another step and they keep advancing in phase, or they keep going back in phase, okay? But let's say I have a spin here and a spin here, okay? What can you tell me, what's going on with these two spins? Do you see anything about these two spins that is noteworthy? Yeah, they're doing the same thing, right? So basically, remember in MRI, we don't get to go and see what each spin is doing. We sort of take the sum of all the spins. So these two spins come into the integral and they appear the same, right? So that means that when I go to reconstruct it, I can't tell if the signal came from here or it came from here. Okay, because from a point of view of what their phases are doing, they're doing exactly the same thing, right? So what could I do to solve that problem? Right, I mean, obviously these spins, this is going this way, and this is going this way, right? But at this time step, at these locations, I can't tell. This spin went this way, and this spin went that way, right? But because of the step I took, I can't tell. I can't differentiate pi from minus pi, right? So what could I do? If you were the MRI engineer or physicist, what would you recommend they do? Yes.
Take smaller steps.
Yeah, take smaller steps, right? So yeah. So now if we look at those two things, you can tell this looks different from this, and this looks different from that, right? Because I took a step this way, and that's different from taking a step that way. All right. So that's the whole idea, that this is the step where you are in k-space going from here to here is some delta k, right? And if I take too big of a step, then I miss the interesting that's happening at smaller intervals, okay? So another way you can think about it is, let's say this is my desired field of view, okay? And let's say I have this really simple object within my field of view. It's all pink here, and it's all green here. And let's say I had a kx that's 2 over the field of view. So that means it does, one period goes from here to here, okay? So that means that that Fourier component repeats, such that this part of the object gets multiplied by exactly the same phasors as this part of the object, right? Because these spins look exactly the same. These phases look exactly the same as these phases. So that means I have no real way of differentiating these two halves as my object, right? Because they multiply by something that looks exactly the same. Whereas if I have kx equals 1 field of view, then this is multiplied by things that are pointing up here, and this is multiplied by things that are pointing down. And so the general rule of thumb is you want one rotation of your phasor across the field of view for your lowest frequency. Okay, and that turns out to be the design rule, that step should be 1 over the field of view. Okay. So it turns out the design rules we come up with are incredibly simple, but very powerful. So now we're going to take a step back, and we're going to remind you a little bit about sampling. So remember, sampling is just the process of going from a continuous waveform to discrete waveform. So typically g of x to g bracket of n, okay? And remember, in mathematically, the way we define sampling is multiplying by a comb function, which is just a train, what's called an impulse train, or a bed of nails, or a Shaw function. We'll just call it the comb function because it sort of looks like a comb, right? And by default, the spacing is 1, okay? But of course, that's not, we want sort of a scaled comb function where the spacing might be sort of delta x. And so we can just rewrite it like that. This is just delta function spaced at delta x, okay? Now, there are these weird factors that come out because of how Dirac delta functions work. We're not going to worry about those too much. We're mostly going to be worried about the spacing, okay? So the spacing here is delta x. And the nice thing about the comb function is the transform of a comb is just a comb. So that's nice and easy to remember. So that just leads me to delta function in kx. And therefore, if I have a cone of x over delta x, then I can use a scaling theorem to say that that's just going to give me a cone of kx delta x. These scaling factors cancel out, and I'm left with this impulse train here, where now the impulses occur every 1 over delta x spacing. Okay. So this is what it looks like. I start off, if I sample in delta x in one domain, whoops. Sorry about that. Let's see if that recovers. Okay, good. If I sample by delta x in one domain, in the Fourier domain, I get 1 over delta x. Okay. So basically, the finer I sample in one domain, the more spread out the impulse train is in the other domain. So that's just the scaling theorem. Okay, so let's take a look at this in the context of what happens. Now, the key thing to remember is in MRI, we're sampling in the Fourier domain, okay, which makes things a little different. Typically, a lot of especially electrical engineers are used to sampling in like the time domain or the spatial domain, like the domain that you're working with. In MRI, you have to remember the sampling is done in the Fourier domain, okay? So let's say my object was a rect function. The Fourier transform is a sinc function. Okay. So this is the signal that I'm going to be sampling, right? So if I sample it like this and take the inverse transform, the question is, do I get back a rect function or not? Okay. So to answer it, let's go back and remember that the Fourier sampling is just simply multiplying by this thing that has a delta k interval. Okay, so we'll just call delta k the interval that we're sampling at. And remember that the sampling is, I take my sinc function, I multiply it by something with a spacing of delta k, and I get my sampled sinc function. Okay, that means in the object domain, it's the same as taking my object, multiplication becomes convolution. Now I can involve with 1 over delta k, right? So this means this is going to reproduce this rect function with a spacing of 1 over delta k. Okay, so you can sort of see where we're going. As long as those don't overlap, I'm okay, right? Because as long as that 1 over delta k is big enough, then I should be able to just chop out the other parts. Okay. So that's basically the field of view. So the first design requirement we're coming up with is based on the field of view. So the user specifies the field of view, and you go, great, now I just know that 1 over delta k has to be big enough such that the field of views don't overlap. Okay. So to avoid overlap, we simply want 1 over delta k greater than the field of view, or equivalently, delta k has to be less than 1 over the field of view. Okay. So this is sort of the design thing you'll want. And in all your problems, and generally in the field, what we just do is we just set it equal. Okay, so the design rule is just set it equal to 1 over field of view. All right. And if you don't, then you get what's called aliasing. Okay, so the most extreme case of aliasing, obviously, is if I just sampled the sinc function with delta kx equals 1, then I just get 1 in all these zeros, right? And this just goes to an impulse, right? We know that the inverse transform of an impulse is just 1. And that makes sense because if I take my square and replicate it with a spacing of 1, all these just bunch up and I just get a value of 1 everywhere. Okay, so the theory all works out. Okay, so any questions on that? That's just sort of a review of 1D sampling. Okay. Anything online? Nope. Okay, so now in MRI, for this course, we're concerned about 2D sampling. So we just need a 2D cone function, which just looks something like this. Once again, a bed of nails. And it has a nice feature, just comb x times comb y. So we can also have things that have spacing of delta x and delta y. And we can have now our 2-dimensional sampling is we take our sort of ideal Fourier transform and we multiply it by this comb function, which has spacing of delta kx and delta ky. Okay, and this just gives me now a discrete waveform where I basically have the coefficients of my Fourier transform at these locations multiplied by the impulse at that location. Okay. So this is what it looks like. Let's say I have, this is my object. Okay. It's a rect function, right? And its Fourier transform is a 2D sinc function, right? So now I sample this with some sampling grid, right? And this is my sampled waveform. So this is a sampled version of this. Okay, and this is essentially the data you would get out of an MRI system. You're going to get points sampled in K-space. Okay. So then we say, well, I multiplied in the Fourier domain. So I'm just going to convolve in the image domain by the inverse transform of this sampling grid, which is just another sampling grid, which now has spacing of 1 over delta K. All right, so I did sampling of delta K here. So now this is 1 over delta K. And each of these, remember when I convolve any function with a shifted Dirac delta function, it just takes that object and puts it where the Dirac is, okay? And so this just gives me these replicas here, all right? And then obviously, if these don't overlap, then we can just take the middle image and we're done, okay? So the Nyquist condition is pretty easy. Basically, we just need that it satisfies these conditions here, okay? And actually, then the design rules are actually just pretty simple. 1 over f of e of x, delta ky, 1 over f of e of y. All right, so for any problems you have or any quiz problems you have, this is all we're asking you to apply. Okay, so let's go to this question here, and I'll open the poll for those online. So this is the object, g of xy cosine 2 pi 3x plus 2y, rect x over 3, rect y over 4. What are the delta kx and delta ky you need to avoid aliasing? Assume everything is in units of centimeters. Okay, so go ahead and take a look at that with a minute or two. You can feel free to talk to anyone around you. I'm going to open up the poll here. Let's see, where's that? Okay, about 30 more seconds. Okay, let's in class at the count of 3, just say really loudly what you think the right answer is. 1, 2, 3. Okay, great. Unanimous C, and C is the choice of at least 2/3 of your colleagues online. So yeah, let's just review that. So what is the FOV in the x direction here? 3, right? Because I got rect x over 3, and therefore FOV in the y direction is 4. So then you just get 1/3 and 1/4. So pretty simple. Okay.
B would also be the right answer.
Sorry, good.
B would also be an answer. I mean,
B could be an answer. Yeah, that's true, but great point. So the idea is that why would you maybe not pick B? Like it's actually a question. Like let's say you were out there, you're working for Siemens or GE or health, whatever, Philips. I don't, all the big ones, Toshiba, Canon, whatever. And you're asked to design the delta K and the delta Y. Why would you not pick B? Yeah, it's going to take longer because your delta K is longer. So now it's going to take longer. Not much longer, right? It's going to be like 20% longer or something like that. But, if you're lying on the table, cutting it by 20%, it matters to you, right? If you're the patient. So that's a great question. So these are exactly the design decisions you make when you're out working in the real world is, this is a great, there are thousands and thousands of MMR methods that have been developed. Maybe 10 to 50 are actually used in practice. What happened to all the other thousands that were developed? Either they're too slow, too expensive, they didn't work all the time, so these are all the things that prevent things from being adopted. Okay, or else it didn't have a good name. Marketing also matters. Okay. So you want to be you want to have delta K small enough to be correct, but not too small, because then it's gonna take more time. So that's a great question, actually. Okay, the other thing we're going to talk about is windowing, which is basically, we've talked about how finally a sample. Now it's for, how far do we want to go out in K-space? Once again, we can go out as far as we want, but it's going to take more time, right? So we don't want to go out too far, right? So we want to go out just far enough that we think we have enough data. So we're going to represent as windowing. So basically, this is the data we require. This is the ideal Fourier transform that we require. If time and money were of no concern, right? We just acquire all data we wanted. But now we're going to say we're going to only acquire data within some window represented by W, and we're going to windowed version of my Fourier signal. And so since I'm multiplying in one domain, I'm going to convolve in another domain. So it means take your original object and convolve it with the inverse transform of whatever this window was, right? So let's take a look at what that does to my image. So let's say this is my object here, okay? And this is a 2D rect function, and now I have a two-dimensional sinc function here, right? I'm like, well, I don't really have time to collect all this data. So I'm going to collect data within this window here, okay? And then this is what my data looks like, okay? So the question is, what is the effect on my image? Well, that means I've multiplied in this domain, so I'm going to convolve with the inverse transform of this, which is now a two-dimensional sinc function. Okay, so I take this and I convolve it with a sinc function. I think in your first MATLAB problem, you convolved it with a Gaussian function. And if you convolve it with a sinc function, you end up with this. So you get some blurring. You also see these sort of artifacts, right? Those are the zeros of the sinc function, right? Okay, so there's obviously a trade-off, right? You're not collecting as much data, but your image doesn't look as good. Okay, so the question is, how much data, what should the size of this rectangle be? Okay, so what we can do is we can answer the question by looking at what is the inverse transform of this rect function. So I have rect with a width of wkx in the kx dimension and wky in the ky dimension. That gives me a sinc of wkxx, sinc of kyy. Sort of ignore these factors for now. They don't really matter too much. So I'm going to have my object convolved with this two-dimensional sinc function. Okay, so it's basically just the mathematical version of what we just said, with the pictures. Okay, so now let's look at the effective width of a sinc function. So we define effective width as, I want to figure out what is the rectangle that has the same area as the sinc function. Okay, and I'm going to call that my effect, the width of this rectangle that has the same height as my sinc function in the same area. I'm going to call that the effective width of my sinc function. Okay, and so we can do that, and we've already played this game before with the RF pulses. No one really wants to take the integral of a sinc function. I certainly don't. So I'd rather use Fourier transforms and say, okay, that's just the Fourier transform of the sinc function evaluated at kx equals 0, which gives me this. And so therefore, the width of my sinc function is 1 over del wkx. Okay. So that means sinc that has this width, sinc with its first 0. So the first 0 of this function is 1 over delta kx, right? That's where wkx, x equals 1 is the first 0, right? And it turns out where the first 0 is actually also the effective width of the sinc function. So that you can just remember that. Okay. So it's nice that it turns out to be so simple. So that means that if I'm in K space and I have a width of wkx, right? That means my effective width, my delta, is 1 over delta kx. Okay. But the tricky part that you have to remember is that width is over plus and minus spatial frequencies. Okay. So I only go out to wkx over 2, and I only ever go out to minus wkx over 2. Okay. So the spatial period, the high spatial period I acquire is not wkx, it's wkx over 2. But that's the highest spatial frequency for a width of wkx. All right. And let's see if that makes sense. Let's just imagine I had an object like this, which was varying like this, right? So you could argue that, well, to resolve this pattern, at least I should be able to resolve the size of each one of these. Okay. And that's my effective width, right? But I could do that with a sine wave that is only half that spatial frequency. It has the spatial frequency is this, right? So something with the sine wave with this frequency and this period. So this is a period of 2 times 2 over delta w, 2 over w gives me the effective width of 1 over w. Okay. So that just means that this 2 over w is essentially this highest spatial frequency that I acquire. Okay. So that's just a factor of 2 you have lurking around when you're doing your homework problems or your projects, that you just have to understand that that's what the design rule takes that into account, that the width is the full width. Okay. So let's just give an example of what happens when you're at the limit. So in this case, I've got delta x plus delta x minus 1, right? So in the x direction, I've got these two things spaced 1 apart, right? So let's say I want my resolution, I want my width to be 1, so I could sort of resolve those two, let's say. That would be the limit. And so that means my wkx should be 1 over w effective, which is 1, okay? And so if I do a sinc with that wk, this is what each of those delta functions becomes a sinc function, right? When it's convolved with it. And you notice the sum of those two just has 1 peak. So at the limit, when I pick that, I can't resolve those two things, okay? But since it's a design rule, it's saying, well, right at the limit, that's the limit where you just can't resolve it anymore. But if I just go beyond that limit and make wk, let's say 50% bigger, so now I go 50% more in K space, you can sort of see we're resolving the limit even better. Now you can actually, the sum of them, you can see this peak and this peak. And if I double where I go in K space, you can resolve the peaks really well. Okay. So it turns out that, resolution is one of those things that is somewhat subjective, right? You can say, I want a resolution of 1 millimeter or 1 centimeter, but then the images come back and you're like, I really want to be able to resolve these two things that are really close together. And so you might actually then have to iterate and say, well, given what I'm looking for, maybe I actually need higher resolution. Okay, so that's a design decision that you have to make. Okay, so let's put it all together. We've got both sampling and windowing going on in MRI. So this is my object. This is Fourier transform. We're doing everything in this domain, okay? We're sampling and we're windowing in this domain. And so I go from this, which is my ideal 2D sink, to a sink that is sampled and windowed. All right, so that's what I have. So now I want to say, well, what did that do to my image? Well, this is all multiplication, so this is all convolution. So it means first, I convolve, or it doesn't matter which way I go. I can do these in either order, but let's say I convolve first with this, so that gives me these replicas. And then each of these replicas gets smoothed out by the sync function, which so each of these is a version of the original, but it's just blurred out a little bit. Okay, I'm not sure we can see that if we blur it. Yeah, you can sort of see it there. It's not quite as sharp as the original. Okay. So that's all, that's it. That's basically what you need to take into account. So basically, sampling in K-space affects your replicas, and you just want to make sure the replicas don't overlap. And then windowing in K-space affects your resolution. Okay. The bigger the window, the better the resolution. Okay. So this is just saying in math what we just said. And so the design rules become that, let's just write down design rules. So basically, delta K is equal to 1 over the field of view. Okay. So basically in the design rules, we just use equality. And then the width in K-space is just equal to 1 over the resolution. Okay, which is what we're also calling the effective width. All right. So in all your problems, that this should be sufficient to do what you want to do. All right. Okay, so let's look at this question here. So here, I think it's the same object, right? So now, what would be a reasonable choice for the resolution of this object, and what kx max and ky parameters would you end up with if you pick that resolution? So this one's a little more challenging, but I'm sure you guys can do it. Okay. So I'll give you a few minutes to think about that, and I do encourage you to, if you have someone you can chat with them. Otherwise, we'll just come back in a couple minutes. About 30 more seconds. Okay, so let's say in class at the count of 3, just go ahead and say really loudly what your choice is. 1, 2, 3. for B and C, which sort of which actually mirrors what's online. B and C are like in a dead heat right now. So, oh, C is pulling ahead of slightly. Okay. So let's see whether it's B or C. Or maybe it's one of the other ones. Okay. So let's say we have cosine 2 pi 3x plus 2y, right? So what's my period of variation in the x direction? How long do I have to go before that cosine repeats itself? 1/3? Okay. Okay, so basically I have a cosine or a sine, the cosine repeats itself in a period of 1/3, right? So as we said before, it would be reasonable to have each of those would be a reasonable size of resolution. So that'd be 1/6, right? So my resolution in the x direction, I would pick it as delta x equals 1/6, right? And the design rule says pick WKX equals 6, right? But remember, KX max equals WKX over 2 equals 3. So we know it's either B or C, right? Okay. And I think if you go through the same reasoning, then you'll find out it's B, right? Okay. You could also have done that by just looking at this is a frequency of 3 and this is a frequency of 2. So that's where you'd want to go. All right. And notice this has no effect on your answer. Okay. Just as in the previous question, this had no effect on your answer. Okay. So any questions on that? Okay. All right. So let's take a look at this is, I think, this is from a GE scanner, although I think you can get this from MRI questions. Oh, I don't remember actually. But let's just go through so all the vendors have a different sort of GUI. This one is actually quite old, but it's at least gets useful for getting the point across. So you sort of see here, field of view is 24. So that means and it's sort of understood as 24 centimeters, okay? Simply because a human head is about, 24 centimeters, okay? So we know it's not meters, we know it's not millimeters because we know what size humans typically are, all right? So that gives me the field of view, but it's only the field of view, and you wouldn't know it, but this is actually defining the field of view in the x direction, okay? And the phase, in this case, the phase field of view is just as 1, which doesn't make any sense, right? Why would I have 24? So this is just a multiplier. This just means field of view in y equals 1.0 times the field of view in x. So that's just a scaling factor. So different vendors do it differently. This is just one way. And then there's nothing here with resolution, is there? I don't see anything about resolution, but I see this frequency and phase, okay? The frequency is 256 and the phase is 128. That's sort of saying I want 256 voxels in the x direction, and I want 128 voxels in the y direction. Okay, so that's also what's called the matrix size. And so from there, you could say, well, delta x then just equals 24 over 256, and delta y is equal to also 24 over 128. Okay, so in this case, the person wants the voxel size in the x direction is half the voxel size in the y direction. Okay, so the resolution doesn't have to be the same between x and y. All right. And in this case, so behind the scenes, and if you actually go and look at a GE scanner, the pulse sequence code, which is not a fun experience, but it's certainly a good. It's sort of like it's certainly interesting to look at it. It's basically you will see these sort of calculations where they're going to go from these parameters and they're going to do something from delta x and delta y. They're going to figure out how far to go out in K space. And then from the field of view, they're going to figure out what the sampling in K space is. Okay, so whatever the radiological technician enters gets translated behind the scenes using basically what we just talked about. Okay. Okay, so that's really, those are the general principles of sampling in K-space. So now we're going to apply to the spin warp pulse sequence. Okay. So remember, this is what spin warp looks like. We have the RF pulse, TR is our repetition time. We play out this gradient on GX each time, and then we change the amplitude of the phase encodes such that we go line by line by line by line through K-space. Okay. Now we want to actually look at an actual sort of, well, an idealized spin warp pulse sequence and figure out how to actually calculate, you know, how big should these gradients be and how long should this be played out for, right? And here, how should I change the size of going from here to here to here to here to here? Okay, so that's the design we're going to go through now. Okay, and so just to show you what's happening, so this is GXGY. In your, I think in your, yeah, in the homework, you're asked to give sort of things like this, where you show GX and GY as a function of time, and then KX and KY as a function of time as well. Okay. And so here, essentially, this KX is just the time integral of this. So it goes negative and then positive, and then GY just goes negative and just hangs out there, or goes at different levels. Okay. So you can sort of see in KX, we're doing the same thing over and over again. And then in KY, we're just going out to different starting points along the KY axis. All right. Okay, so let me see what we're doing. Okay, so there's one additional thing I need to tell you, which is essentially, how do we sample in KX? Okay, how does the sampling actually get done? Okay, so this stepping from here to here, that's sort of, you can sort of see here, that's getting me my steps in delta KY, right? The spacing of those lines is the sampling in delta KY. But then as I go along the line, I'm acquiring samples along KX, right? So the question is, how is that sampling done? So it turns out, without going into too much detail, we talked a little about the RF signal comes in, we demodulate it, right? This is multiplying by e to the j omega naught t, right? Okay, so this isn't how it's actually necessarily done all the time, but this is sort of a good representation of it. And then we apply it through an analog digital converter, okay, which both quantizes and samples it. So basically takes my continuous wave signal, gives me samples every delta t, let's say, and then also turns it into a digital number. Okay, so those of you, certainly if you've in EE, you probably heard of analog digital converters. They're basically, you know, everything in the world is basically an A to D converter or D to A converter now, right? Basically, you need something on your iPhone, you've got an A to D converter that takes your voice, you know, and converts it to digital, and then you've got a DA converter that takes everything and makes it audio, right? So everything, your camera, your voice, everything. So A to D converters and D to A converters are very useful, and also in MR, incredibly useful. Okay, so let's start off. And I'm going to preface this by one thing, just to remind you, especially for the homework, spin warp does not equal square spiral. Okay. So luckily, the good thing about the MATLAB grader problems is they give you instantaneous feedback, right? So if you get it wrong, it's wrong, right? And you can do it as many times as you want. Previously, you would have to wait for the graders, the TAs to grade it, and you would realize, oh, I did it wrong, okay? And the most common mistake previously was people tried to apply what we're doing, the spin warp example, directly to square spiral. And the principle, the fundamental design rules apply, but how you apply them is slightly different, okay? So that's just a warning, okay? If you try to take what we're doing in class today and apply it and use that to solve the MATLAB grader problem, it just won't work out. Okay, so you need to think back as like, what do I need for my delta K? What do I need for my width and things like that? Okay. Okay, but with that warning in mind, let's just talk about the sampling in the KX direction. So remember, we've basically got this waveform here that's taking us out to some starting point, and then I come out to some starting point here, and then I zoom back across here. And then as I'm doing this, as I'm traversing back along K-space, my ADD converter is acquiring a sample every delta t. Okay. So it's essentially giving me the average signal in that interval of delta t. Okay. So then if I know the size of this gradient, GXR, well, I can say, well, delta KX is just gamma over 2 pi times the incremental area under that gradient. So every step gets me some little area, right? And so that's just GXR times delta t. And I know the field of view is 1 over delta KX. So if I know field of view and I'm given one of these, then I can always figure out the other one. Okay, just by solving those equations. So let's look at an example of this. So let's say the user said, I want the field of view in the X and the Y direction to be 25.6 centimeters and delta X equals delta Y equals 0.1 centimeters. Okay. So here we know that even though we're giving all these things, really, if I'm trying to figure out, let's say the delta K, I only have to care about the field of view, right? The other parameters doesn't matter to me at this point. Okay. So let's say, so we know the field of view is equal to be 1 over delta K, which is gamma over 2 pi GXR times delta T. And let's say you're just given delta T equals 32 microseconds. Okay. So for this class, we'll typically give you one of those parameters. In the real world, it's a little more, there's some design trade-offs. You can pick, typically the manufacturer will give you some delta T's. It's sort of, if you go back to that previous slide, you'll see a bandwidth parameter, and you can sort of play with that. And we might get to that later on how you pick that, but for now, just assume you're given that. So I'm given delta T, so I can solve for GXR. I basically just plug and chug, and I would get, in this case, GXR equals 0.28675 Gauss per centimeter. Okay. So what is that? That means that's a field that within 1 centimeter changes by 0.2528 Gauss. That means in 1 centimeter, it would change by half a Gauss approximately for the Earth's magnetic field. So it's a fairly tiny change in the field. Okay. Okay, so let's now look at resolution in the X direction. Okay. Resolution, remember, if I've given a resolution, that tells me what to make of how to make my W parameter, right? My width parameter, and that's equal to, the width is equal to 2 times KX max, which is my maximum frequency. And so we know that that's going to be equal to, this width is just gamma over 2 pi GXR times the total length of this waveform, right? Because this waveform takes me all the way from here to there. So it takes me all the way, this width is from here to here. And so I know this area, is going to give me my delta KX. And I already solved for GXR, so now I can just solve for tau sub X, okay? And so we do that, the tau sub X, we say delta X equals, this is the 1 over WKX, right? And we know that that's equal to gamma over 2 pi times GXR times tau sub X, okay, which is the full width. And so if I plug that in, I get it equals 8.192 milliseconds, okay? And this just turns out to be 256 times delta T, okay? So this equals 256 times delta T. That means I have 256 steps, 256 of those little increments in that time window, right? Which makes sense because if you go back to the original design criteria, look at this. The number of samples I have is actually FLV of X over delta X, and that's 256. Okay, so for basic MRs, quick sanity check is the number of samples you want in the X dimension is equal to the number of samples in the KX dimension. That's if you don't play any tricks. As we'll see later, the idea is I don't want to take that many samples. I want to go faster, right? So then you start playing tricks, okay? But if you're not playing any tricks, you're just doing plain vanilla Fourier-based MRI, then that's a good rule of thumb, okay? I mean, it's also a good rule of thumb. If I only want, let's say, 256 samples in the X direction, I never want the number of samples in KX to be bigger than that, right? Like if my answer turns out to be, I need 1,000 samples in K space to get 250 samples in image space, then you know the calculation must be wrong. Okay. Okay, so let's do, I think we have time for, yeah, why don't we do this problem since I think it'll be useful. So you're asked to design a spin warp gradient readout gradient to achieve field of view equals 20 centimeters and resolution 2 millimeters. The maximum gradient strength available is 2 Gauss per centimeter, and the readout sampling is, so this is the delta T, right? 5 microseconds. What should be the amplitude of the readout gradient? And by that, I mean this gradient here. Okay, that's the readout gradient, that flat part. Okay, so this is the GXR, and this is the delta T, right? Okay, and to keep things simple, you may assume that gamma over 2 pi equals 4,000 hertz per Gauss, and you're just asked to pick the closest answer in case the answer doesn't quite work out. Okay, so go ahead and let's do this problem. Oh, yeah, okay. So after this problem, I've been reminded we'll talk about the project. Okay. To see what's next there. Yeah, that's a good place to stop. Okay. Okay, about 30 more seconds. Okay, at the count of 3, just say what you think the best answer is. 1, 2, 3. F. Okay. F was one of the least popular answers online, 17%. So this will be exciting because I don't even remember what the answer is. So let's figure it out together. Okay. So clearly I don't care about the resolution, right? I just care about F of V, right? So I want delta K X equals 1 over 20 centimeters, right? And we know that's going to be equal to gamma over 2 pi times GXR times 5 times 10 to the minus 6 seconds, right? And this, we're told this is 4,000 hertz per Gauss, right? So we know GXR is going to be equal to, let's see, 1/20 times 4 times 10 to the 3 divide, and then also 5 times 10 to the minus 6. Is that right? Okay. So then I have, let's see, I have 1/80 times 5 times 10 to the minus 3 equals 1,000/80/5. That equals 200/80, which is greater than 2, right? So yeah, it is F. Good job. Okay. All right. So yes. Okay. So any questions on that? Okay. So as you can sort of see, at least at this level, the design equations are fairly straightforward, but just a reminder, it's the principles that you want to apply for the homework, not these exact equations. Okay. All right. Anything else before we move on to discussing project 2? Okay. So let me go to this. Can you guys see that okay? Yeah. Okay. So the project 2 will be held during the 3-hour exam period that we would typically do for final exams. And so since that's 3 hours long, we have slightly longer for each presentation. So we're suggesting that you have roughly 9 minutes plus 3 additional minutes, which is a total of 12 minutes per group. Wait, this is the wrong one. Sorry. It's project 1. Okay. Project 2. Let's do project 2. Oh, there we go. Okay. Yeah, so that's going to be okay. So one thing is that by default, the group composition that we're going to start off with is what you had as for project 1. Let me fix that. Project 1. Okay. Gee, why did it do that? Okay, let's see. All right. Well, let's just.
We can update it.
Yeah, we'll update that later. I'll send you the updated thing. But anyways, so this should be project 1. But if you feel like you need to change groups, just please coordinate that with either me or the TA. Better, how about send an email to me, Amin and Mary Luz, and so that way everyone's in the loop. If you presented a recorded project for 1, you must be part of a live group for project 2. Even if you switch groups, you can't use switching groups to like get out of a live project, okay? Which I'm sure nobody wants to do, but just in case. And if you did present live for project 2, then you can be part of a live or record group for project 2. So we give you that option, right? If you really want to, some people really like to be live twice, okay? So now we're allowing you to give a 12-minute presentation with 2 additional minutes, so about 14 minutes per group. Okay, let's keep it to that. It's recommended you have about 12 content slides. And so here the main thing is send an email to these 3 addresses with your group number and a short project proposal by 11 a.m. on Wednesday, November 29th, 2023. Okay, so next Wednesday. And basically what's going to happen is because the MRI ones are sort of more generically described, I will be looking for at least a few sentences on what you plan to do. If you plan to reference a paper, attach those papers. I will look at your proposal and I will give you some short feedback. Typically, I'll say, yes, sounds good, but maybe focus on A, B, and C. Okay. If your project is too similar to another group's, first come, first serve. So if you're the second to present it, I'll say, that's a good area, but this is already being done here. So I want you need to focus on some other things. And then you can submit a revised proposal if you want. Okay. The idea is we're going to try to get all that sort of taken care of by Sunday, December 3rd, in which case, all the groups and everything will know all the groups, who's going live, who's going recorded. So that still gives us like 8 days or 9 days before the actual thing. And so then there's buffer time in case we need to swap around. Okay. So any questions on that overall logistics before we go into some more details? Okay. Yeah, upload to YouTube. there were a bunch of recorded presentations where it was hard to see part of the, you know, the slides because the speaker panels were covering the slide. So just, in Zoom, you can adjust that through the recording preferences. And the recorded talk should be at most 12 minutes. Typically, once it goes past 12 minutes, we're not really paying attention. So, just realize that, make sure that recording, okay? So let me just give you a few, this is the grading criteria. It's slightly different. We're putting a little more focus on difficulty here, 15 points. The background material should also, I think overall, just, we do want to make sure that there's a clear connection to course content. And so if, for example, you're doing a simulation, that simulation should be, or you're doing like a deep learning segmentation, there has to be something about that deep learning aspect that requires something that's related to MRI, okay? It's not sufficient to just have a background that talks about MRI and then just do something that's totally unrelated to MRI for your thing. That will just get you deducted points on sort of connection to course content. So I just want to make that clear. Definitely recommend that, you strive for some level of difficulty because it is worth more now, 15 points. So either computational component or something similar level of effort, like, deriving a new theoretical result. Or if you're presenting existing theoretical result, then we're not looking for simply you to present the equations that we could already read in the book, right? We want you to either give us new insight into it or present it in a way that makes it like crystal clear. Like, like on YouTube, you see examples of that. Like has anyone here heard of like 3 blue, 1 brown? There's just great examples of, or physics with Elliott is also great. I mean, there's these guys who just, present stuff really well. So if you can do that, then that would certainly, meet presenting a existing theoretical result in a better way. For background material, don't spend too much time on extraneous non-technical background, right? For example, this is not a course about COVID or about, liver disease. So we don't need 3 minutes about liver disease or anything like that, okay? Also, don't spend too much time reviewing material, although it always flatters us when we see our slides used again, but we don't need to see them again, okay? So basically, if it's in the book or in the slides, you don't need to repeat it again, okay? Accuracy, just make sure what we're really looking for in that is, do your results justify your conclusions? It's exactly what you're going to see in either work doing a PhD or out in the outside world. Your manager advisor is like, hey, is what you're saying actually supported by your data? Presentations, show, don't tell. Okay, you probably heard this before. It doesn't really help to have a slide with like, sorry, this is a slide with lots of words, but it's a little different. So we don't want you to read off like, 5 sentences, right? Show us what you're talking about. Use your mouths, show us, hey, this is bigger, or that's bigger. So these are just reminders. This is an example of a strong project for 2021. If we might try to post some other ones for you to look at, but this was a particularly strong one that you can look at. Any questions on that? So that's just general advice. Let me see, there is something in the chat. Let me see if I can address that. Will the topics or some kind of prompt be given to us like project 1? Yes, perfect. Okay, so I didn't even, that's a perfect segue into this next thing. You have a lot more freedom on this one in some sense, in the sense that you can do any MRI related project of interest to you. And basically all I've given you is a list of potential topics, which there's much more. You're not limited to these. You can also, if you feel like you just want to do something that is rigorous and would satisfy the requirements, you can pick one of these projects, okay? And you'll see that, it was, in some sense, these are, everyone had to do these projects, when this was offered in 2008. So there was a lot, these are quite rigorous projects to do, but if you do those, that you're going to at least hit, a lot of the difficulty criterias. There's a lot of resources with software and code that's out there. So I've posted some here. This is not a comprehensive list. You all have Google, you all have ChatGPT. So, I don't need to tell you everything about what's out there in the world, but that's certainly some, not all. I haven't double check to make sure all these links still work, but if one doesn't work, you can use Google to find out where it is. Okay. So with that, I encourage you to pick something that's of interest to you. Start early so you can sort of figure out what you're going to do, and then submit the proposal by next Wednesday. Okay. So any questions about the project in class or online? Okay, great. So I think we've gone a little past today, but hopefully that was useful for you. And I'm here to answer questions. And otherwise, we'll see you on Wednesday, or some of you on Wednesday.